the problem that I'm going to be working through here is going to be the similar problem that you are going to be solving and thinking about in your lab activity for this week. Okay, so that's why we're working through it in the pre-lab. So we have a ball of clay and it's dropped from a height of 1 meter. Okay, so we'll call that point A. It strikes the ground here at point B. We're assuming it's falling vertically, but I'm just drawing it like this. Okay, it strikes the ground at point B, and then it rebounds, it bounces off the ground, and it returns to a height of 0.35 meters. How much energy was lost when the ball struck the ground? Okay, how much energy was lost in this process? Okay, so when our ball is up here before we drop it, it only has gravitational potential energy. Our gravitational potential energy is mass times gravity times its height above the ground. Okay, when it strikes the ground, or at the very instant moment just before it strikes the ground, it has converted all of that gravitational potential energy into kinetic energy. Okay, and then the ball strikes the ground and then it rebounds. It bounces off the ground and it goes up to a final height. Okay, now if energy were perfectly conserved, then all of that gravitational potential energy would be converted to kinetic energy, and then it would be converted back to gravitational potential energy again, and then the ball would return to the same height from which it started. But we're losing some energy in the system. So after our ball strikes the ground, it ends up with some height that is not the same as the height from which it was dropped, which means that there was some energy that was lost in the system. And we want to figure out how much energy was lost. So, you know, the ball striking the ground here, it makes a sound. The ball itself is going to be deforming. It might deform the ground a little bit too. There's going to be maybe there's some heat energy that we lose too, due to friction as it falls and friction as the ball strikes the ground. So there's a lot of places where we can lose energy, and we're going to figure out how much energy did we lose. Okay, so if we're going to compare just the energy that we lost during the collision, that means that we're going to compare the energy, or the gravitational potential energy that the ball has when it's here at point A, and then the gravitational potential energy of the ball when it's here at point C. Okay, so we find the gravitational potential energy at both of those places and compare them or subtract them, and we'll see how much energy we lost. Okay, so the energy that we lose in this system after the collision with the ground is going to be equal to the initial gravitational potential energy minus the final gravitational potential energy. Okay, this energy that's lost, that's different from our change in potential energy. Change in potential energy is your final potential energy minus your initial potential energy. Here we're looking how much energy did we lose, which we take the gravitational potential energy that we had to start with minus the gravitational potential energy that we end with. That's different from when I ask for the change in gravitational potential energy. Okay, different by a minus sign. Okay, but it's still different. So here, let's see how much energy we lost with this collision on the ground. Okay, so we start with our gravitational potential energy that we had to start with, which is mass times gravity times our initial height minus our final gravitational potential energy here at point C. So this was at point A, this is at point C. And so that's going to be minus mass times gravity times our final height above the ground. Okay, so I'm just going to pull out my mass times gravity. So it's going to be mass times gravity times our initial height minus our final height. Okay, so the energy that we lose is the mass of our ball, which I didn't tell you. The mass of our ball is 0.1 kilograms. Okay, so we've got 0.1 kilograms, which is 1,000 grams or 100 grams, times 9.8 meters per second squared, times our initial height, which is 1 meter, minus our final height, which is 0.35 meters, okay? So then we see that the energy we lose in this collision is 0.637 joules, because joules are the unit of energy, okay? So how does this compare? So this would be the answer. That's how much energy we lose. But just to think about it, okay? And you're going to have to think about this for the lab too. How much energy did we lose in this collision relative to our original potential energy? Because it's like, what does that number even mean if we don't have anything to compare it to? So let's compare this number, the energy that we lost in our collision, with our initial gravitational potential energy. So let's do this. Let's take the energy that we lost and divide it by our initial gravitational potential energy, okay? So we lost 0.637 joules. Then on the bottom, we've got our initial gravitational potential energy, which is our mass, times gravity, times the height we started from, which was 1 meter, okay? So this is 0.637 joules divided by 0.98 joules, okay? So our units of joules cancel. It turns out that, so we do this ratio, it tells us the percent of energy that we lost in our experiment here. And we ended up losing 67% of our original gravitational potential energy. Okay, that's almost 2/3 of our initial energy we lost in this collision. And you can, since I started with a height of 1 meter, I'd have no energy lost if after the collision I bounced back up to 1 meter. I'd have half of my energy lost if I bounced back up to 0.5 meters. And here I'm almost back to 0.33 meters, just a little bit beyond that. So I almost lose about 2/3 of my energy through this collision.